Hello everyone. This is going to be our last lesson in the quantum unit. It is a lesson on chemical bonding and it's about the hybridization of carbon. So first of all, just to go through a little bit of the theory, hybridization is a special type of bonding and it will occur with atoms that have underfilled valence shells. So what does that mean? It means that they do not have enough single electrons to form the number of bonds that they need. So for example, carbon needs 4 single electrons, but when you look at its energy level diagram, there will not be 4 single electrons available to create those bonds. So there are 3 elements that do undergo what's called hypo, meaning underfilled, hypovalency. Beryllium is one, boron is the other one. So up to this point, we've always made the assumption that beryllium and even boron as a semi-metal, because they're in group 2 and in group 13, that they bond ionically with non-metals, but that is not the case. In fact, beryllium and boron are considered to be the outlaws because you assume them to be metallic when in fact they behave like non-metals, and both of them will bond covalently with nonmetals, no ionic bonds with them. And then the other one is carbon, and we know carbon shares electrons to form polar and nonpolar covalent bonds. So in this lesson, we're only going to be looking at carbon because we've done the organic chemistry, and it's important to know how carbon forms bonds to make all those organic compounds that we looked at. So what we need to do is create what's called a hybrid orbital. And so a hybrid is a mix of 2 other orbitals. So for an example of a hybrid non-chemistry, think of your trilliums. So you have white trilliums and you have red trilliums, 2 very different colors. But if you hybridize them, where you mix them together, you can create a mix of the 2, which would be pink trilliums. So your pink trilliums would be a hybrid of your white and your red. Well, that's exactly what we're going to do with carbon, is we're going to take s orbital electron and your p orbital of electrons within the same shell, and we're going to mix them together and create a hybrid orbital that is somewhere in between the s and the p orbitals. So in order to do that, we need to take an electron from the s and promote it. So give it a promotion up to the p. So we're going to give it more energy and put it up to the p. It's still within the main shell of carbon. So that's why it's not a transition. It's just a promotion. So you're going to have an electron in the s with lower energy than the electrons in the p that have higher energy. But when you mix them together, you're going to get the hybrid orbitals coming out somewhere in between the s and the p. And what that does is it creates 4 identical single bonds. It can allow double bonds to be identical and triple bonds to be identical. And identical means these hybrids have the same shape, bond angle, bond energy, and bond length. So let me show you what this looks like. So let's start with single bonds. So if we were to look at carbon, carbon is a 2s with 2 and a 2p with 2, okay? Because carbon is over here, 2s, and then 1, 2 over in its 2p orbital. So you'll notice that carbon is supposed to form 1, 2, 3, 4 bonds. It should have 4 single electrons, but we only have 2. So this is why it's deemed underfilled. So to get the 4, and to get the 4 to be 100% identical, we have to promote and hybridize. So we're going to take this electron down here in the s, and we're going to promote it up here. And then what we're going to do is we're going to have an electron in the s, the p, and the p. So each of these has an electron in it. Okay? And then what we're going to do is we're going to hybridize. So we're going to take all 4 of these and we're going to hybridize them, mix them together, and create 4 identical hybrid orbitals, which is a mix of the s and the p. So just like your trillium, if you had a white and 3 reds and you mix them together, you're going to get 4 pinks. So pink is the name of a mix of a white and 3 reds. So for an S and a P and a P and a P, the name is just going to be a combination of all of them. 3 p orbitals with an S. So we call them sp3s. Okay? And they are identical in every way. So the shape of these are half bow ties. Okay, they're half the shape of a p orbital. That's what they look like. Why? That's just the way it is. Okay, so if we had 4 of these little teardrops, if you want to call them that, together, and we want them to be as far apart as possible, what we'll have is we'll have we might have one like this, one like this, one like this, and one like this. And so what you'll notice now is if you go to your Vesper chart, 4 of these with no lone pairs is going to be tetrahedral at 109.5. So this is tetrahedral at 109.5. So what does that mean? It means that your carbon will have a single bond, single bond, single bond, single bond that are 100% identical in shape. So tetrahedral, 109.5 degrees, same bond length, same bond energy. Okay, and then you can bond 4 other elements off of that. So if you want to create 4 single bonds, you need 4 hybrids. This is their shape, and you draw them so they're far apart as possible, and they will always be tetrahedral. So 4 single bonds on a carbon gives you a tetrahedral shape around that carbon. If we go to double bonds, so we're going to have a 2s with 2 and a 2p, 1, 2, 3. So again, we're going to promote, oh, sorry, I just realized I promoted too quickly. So we're going to promote this one up here. And now we're going to have an S plus a P plus a P plus a P. But this time you need a double bond. So to have a double bond, we can't have 4 single bonds. So what we're going to do now is only mix 3 of them together. We're going to hybridize these. And when we do, we're going to get 3 sp squareds this time, an S, a P, and a P. And then this P here does not go in that mixing pot of hybridization. It stays out as a normal looking P. So how do we create double bonds with that? Well, if we were to look at drawing these, sp2s and sp3s have the same shape. They're this half bow tie shape. What we're going to end up with is, so these are identical. Okay, these ones here. So what we're going to end up with is one here, and one here. And when you go to Vesper, on your Vesper chart, 3 of these bonds with no lone pairs is this one here, trigonal planar, 120 degrees. So whenever you go to make these double bonds, you need to make 3 sp squareds. They're trigonal planar at 120 degrees. So if this is your carbon sitting here, you'll have a bond out here that maybe goes to an H. You'll have a bond out here that maybe goes to an H. And then you're going to have one bond coming out here. But this represents only 3 bonds off of carbon. We need 4 bonds, and we don't want 4 singles. We need a double in here. So to create the double bond in here, this is where this comes in. So this P here is the shape of a normal P. But because it's in a hybridized atom, what we're going to do is draw this in, but we're going to draw it in dotted or hashed. So it's going to look like this. So I'm going to draw in that p orbital like this, and I'm going to put that electron there. And now we have a double bond. So that double bond is made with, so this is an sp2, an sp2, an sp2, and this is a p. Over here, this is an sp3, an sp3, an sp3, and sp3. So to make a double bond, you need 3 of these sp2s, and then you need an unhybridized p orbital. So this here is called a pi bond, and these here are sigma bonds. So all 3 of these are sigma bonds. So hybridized orbitals are called sigma bonds. So if you want to make 4 single bonds, you need 4 sigma bonds, hybridized sigma bonds. You mix all 4 in the pot, you get 4 coming out on the other side. The name matches what goes in, so what goes in is what comes out, and they are tetrahedral in shape. If you want a double bond, you mix an S and only 2 P's together, leave 1 out, 3 mixed in, 3 come out. The name just comes from what went in. They're all identical. They have to, when you draw them in, you draw them as far apart as possible. That gives you a trigonal planar shape. And then you have your P orbital that you left out. That forms the double bond. So a double bond is made from 1 P orbital with 3 sigma bonds, which is what we have here. So you can imagine then if we go to a triple, we now need 2 pi bonds, so we're going to leave out 2 of these and only mix 2 together. So going over here, 2p1, 2, we have 1, 2. So what we're going to do is take this electron and we're going to promote it. So now we have an S plus a P plus a P plus a P. But this time, we're only going to hybridize 2. And when we do, we get 2, and their name is just going to be SP. And then we'll have plus P plus P. So these here, this is a pi bond, and this is a pi bond, and these here are sigma bonds. They're hybridized. So if we have 2 sigmas, to put them as far apart as possible is basically going to look like this. So it's going to be linear at 180 degrees. So we're going to have 1 out here and 1 out here. So those are your 2 sp hybridized orbitals. They are linear at 180 degrees. So the shape comes from your sigma bonds. Okay, so the sigma bonds determine shape. And that's because we know, according to VSEPR, double bonds act as a single bond when you're looking at the VSEPR shape. So it doesn't matter that there's pi bonds in there. So now we have to, so we know now, where's my pen here, that if this is your carbon, we'll have a single bond here and a single bond here. But how do we make a triple? So what we're going to do is let's dot 1 of these in up here and bring the other half of the P. So there's that one. So that forms this bond, say to another carbon. And then we're going to bring the other one in down here. So you're just drawing in P orbitals, but you're just dotting them in because they come from, they're made, we're using them after you've hybridized your orbitals. So now you have this here. So what you can see is that a triple bond, so this is now a triple bond, is made from an sp, a p orbital, and a p orbital. This is a pi bond, this is a pi bond, and this is a sigma. Okay, so if you want to make a triple bond, you need 2 p orbitals and 2 sigma bonds. Okay, whereas over here, you need 4 sigma bonds. So you can see you go from 4 sigma bonds gives you 4 singles, 3 sigma bonds and a pi gives you a double, 2 sigma bonds and 2 pi's give you a triple. And so now you've got carbon here that you can put an H over here and then triple bond it to another carbon. Okay, so what we're going to do is let's apply this to examples because that will really help with the understanding, I think. Okay, all right, so the examples we're going to do are we're just going to work through these ones here. Okay, so you have the sheet in front of you. So you can have a look at that. So hybridization of carbon. Okay. All right. So the first one we're going to do is CH3Cl. So let's draw the electron dot diagram of this. So we're going to have a C with 4 bonds or 4 electrons on it. We'll put an H up here, an H over here, an H over here, and the Cl has 7, like that. Okay. And then we can very easily see we'll have this, 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 and this. Now, before we get to our Lewis diagram, we need to show the hybridization of this. What did we do to hybridize this? Well, we have 4 single bonds. So we took a 2s with 2 and a 2p, like that. So this shows that we should only have 2 singles, but we know carbon needs to have 4 singles. So what we're going to do is we're going to hybridize up here. So we're going to get an S plus a P plus a P plus a P. And because we want 4 single bonds, we need 4 sigma bonds. And they're called sp3s because we mix together an S and those P's there, okay, to give us an sp3. So you need to show this if you're asked to, okay? Otherwise, you might have to do it on paper to figure out what it is you need. But anytime you have 4 singles, you need 4 sp3s, okay? So let's go to Vesper. So to draw the Lewis diagram, we already know that 4 sp3s is tetrahedral. Well, look at what we've got here. We have 4 single bonds and 0 lone pairs. So 4 single bonds and 0 lone pairs is tetrahedral. So you already know that this carbon is going to have a tetrahedral shape. And the angle for that is 109.5. So there's your Vesper. So now we're just going to draw it. So we're going to have a C to an H, to an H, to a Cl, to an H. So there's your Lewis bond diagram for this organic compound. Molecular polarity. So if we have positive, 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 negative, because chlorine is more electronegative. We remember from the last lesson, molecular polarity is positive to negative. So it's going to go this way. So we have a net dipole. That's going to be greater than 0. This is polar. Okay, so now let's do the valence bond diagram. So let's start with the carbon. What do sp3s look like? Well, we already know 4 of those half bow tie shapes, each with an electron. So we'll have 1 here, that's this one. 1 here, that's this one. 1 here, that's this lower one. And 1 over here, that's that one. So there is your carbon with 1, 2, 3, 4 electrons. And you remember the shape of a hydrogen? A hydrogen is the 1s. So we'll put this in with 1, this in with 1, this in with 1. And then what does chlorine bring in? Well, if we go to our periodic table, chlorine is here. It has 7 electrons. It only needs to gain 1. So its P has 5. It needs 1 more. So this p orbital here, this one's full, this one's full, this is the s, this one here is what needs to participate. So we're going to bring that p orbital in with its 1 electron, and then a pair from one of the p's, a pair from one of the p's, a pair from one of the s for the s, and that is your valence bond diagram for chloromethane, which is what this compound is. Okay? So let's go to the second one. The second one on your sheet is an amine, CH3, NH2. And the nice thing is we've drawn these to death in the organic chem unit. So these are pretty straightforward. So we're going to have a C with 4. We're going to put an H up here, an H over here, an H over here. And then we have an N with 5 valence electrons. So we'll do 1, 2, 3, 4, 5. And then that has 2 here, 2 H's off the N. So we bond, 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 bond. Okay? Now, the carbon is hybridized. Okay, the nitrogen is normal. You don't hybridize any other element but the carbon, because nitrogen forms 3 bonds because it has 3 singles. Carbon's supposed to form 4 bonds, but it only has 2 singles. So what you're going to do is, for your carbon, show your hybridization, just to make sure that you know what it is that you're doing. We're going to promote up here. We're going to take an S plus a P plus a P plus a P. We want 1, 2, 3, 4 single bonds. So we're going to mix these in the pot. We put in 4, we take out 4, but they're all identical now with an identical name, and the name is just named after what you put in. 3 P's and an S. Okay, so now let's go and do our Vesper shape. Well, we already know that the carbon is tetrahedral. What about the nitrogen? So the nitrogen has 3 single bonds and a lone pair. So 3 single bonds and a lone pair, and it's trigonal pyramidal. So we need to draw this where it looks like a pyramid, and we need to draw this so it looks tetrahedral. So right now, the way this is, this goes straight across. So we know that this H has to come down here, and this H has to come down here. So if that that bond here has to come down here, which means we're going to take this carbon and we're going to rotate it slightly. So we're going to have a C up like this to the N, down to the H, down to the H, and then this comes up here, up here, up here. So with tetrahedral, it doesn't have to look like a T. You can rotate it. So you're just going to take this here and rotate it slightly so that this bond comes up here, this bond is down, this one's up, this one's down to the right, and that allows you to get your trigonal pyramidal shape for this amine. So the carbon is tetrahedral at 109.5 degrees. The nitrogen is trigonal pyramidal, and the trigonal pyramidal shape is 107.5 degrees. And now let's look at molecular polarity. Well, we already know that carbons and H's, that this is positive, 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 and negative. So we know our net dipole has to go up towards the nitrogen, either up this way, up this way, up that way. So this and this. So these 2 dipoles would cancel. This one heads towards carbon because carbon's more electronegative than the C. This one heads up here. This one heads up here. And this one heads up here. So this is what you have. You have 1 here, 1 here, and then you've got 1 here, and then you have 1 here. So these 2 are these 2. This one is this one. This one is this one. So notice your net is going to be roughly in that direction. So we're going to take our net dipole and draw it something like that. So our net dipole is greater than 0. Therefore, it's polar. Okay, so it's going up towards the end, not straight up because you have the extra push in the right direction. So take your straight up and just twist it slightly. Okay, so that's what that one would look like. Valence bond diagram. We have 4 of these sp3s. So we're going to draw them to get this shape. So this time we're going to draw 1 here, 1 here, 1 here, and 1 here. Okay. And then we can put on hydrogen, hydrogen, hydrogen. So hydrogen, hydrogen, hydrogen. And now our nitrogen. So what does the nitrogen come in with? Well, when you go to your periodic table, nitrogen has 1, 2, 3 half-full P's. So we need to draw in 3 half-full P's. 1 is going to go to this carbon. So that's this one. 1 will go down to this H. That's this one. And 1 will go off to this H. That's this one. And then you have your lone pair up here. And then go back and add an H here and an H here. And there's your valence bond diagram for methanamine. Okay? All right, number 3. All right, number 3, where's my sheet here? The last of the single bond ones we're going to do is, this one has 2 carbons in it, CH3, CF3. So we have 2 carbons. So one with 4, another one with 4. One of them will have 3 H's on it. The other one will have 3 F's on it. And fluorine has 7 valence electrons. Okay, bonding pretty straightforward. Here, here, single bond between the carbons. Okay, now what you should notice is both these carbons are hybridized exactly the same way. So both C's equal 4 single bonds. So both C's would be a 2S, 2P. We're going to promote here. We're going to get an S plus a P plus a P plus a P. And we're going to mix these all in the pot. And when they come out, they'll come out as 4 sp3s, okay, for both carbons. Okay. So if we were to look at our Vesper shape, we already know that 4 sp3 is tetrahedral. These are already drawn like that, so this is really straightforward. We're just going to do it like this. Put our F on, an F here, an F here. We don't need to tilt these or twist this in any way because both of them from the electron dot diagram are already in that tetrahedral shape that we have. And so let's write that down. So both are tetrahedral at 109.5 degrees. And the net dipole, you should already be able to figure that one out. The fluorines are all negative, and hydrogens are positive, and you have to go positive to negative. So you could already see that if you were to put in the little dipoles, this goes this way. This is nonpolar, so you wouldn't put a dipole in there. This goes here. This one, sorry, wrong way. This one heading to fluorine, this one heading to fluorine, those two would cancel one another. This one heading to C, this one heading to C, these two would cancel one another. So basically what you've got is these are gone, this doesn't exist. This one up and this one down, when you overlap, they cancel. So your overall net is going to be this way, towards that end fluorine. This is a polar molecule. So this would align an electric field in that direction there. So now if we were to look at our valence bond diagram, we now have 4 of these sigma bonds for each of them. So let's start with this first carbon. So what we're going to have is a sigma, 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 sigma. Okay, and then what we're going to do is bring in hydrogen, hydrogen, hydrogen. So now we have our 4 sigma bonds, each with an H, an H, and an H. And now we're just going to repeat that for the other carbon. So the other carbon overlaps here. So there, right here, is your sigma bond with the other C. And then we'll have one here, and one here. And then fluorine. Well, what do you know about fluorine? Well, fluorine is like the chlorine we just did. It has 1 half empty P. 2 of them are full. So when you go back up, the S is full, the other 1 P is full, the second P is full, and the third one is sitting there half empty. So that's the one we're going to draw in. One here with an electron, one here with an electron, and here with an electron, and then you just put on the pairs. And that is your valence bond diagram for this particular compound here. Okay, and there you can see you have your sigma bond attaching the 2 carbons together. Okay, so those are some examples of singles. Let's do some doubles here for practice. So number 4, Let's do C2BR4. So again, we have 2 carbons. Okay, and we have 4 bromines. So it should make sense that 2 of them have to go on one of your carbons and 2 on the other one. So let's put 1 up here. And bromine has 7 valence electrons. 1 here. 1 over here. And we'll put 1 up here. And what you'll notice is you have to form a single bond between the carbon and the bromines, because the bromine only has 1 valence electron, and that leaves you with this double bond here. Okay, so each carbon, so when you cover this up, this carbon has sigma, 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 pi. There's a double bond in here, so you're going to make 3 sigmas this time and leave out a p bond. This one, same thing, sigma, 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 pi. So for both carbons, you have a 2s and a 2p. You're going to promote S plus P plus P plus P. But this time, you're only going to mix 3 of them in. So you're going to have 3, and now the name changes from sp3 to sp2, and this P. So this is for both carbons. Okay, so this will be helpful when we do the valence bond diagram. So let's go and look at Vesper. We already know that sp2s are trigonal planar, so look at, and it's around each central atom. So look at this first C. Remember, double bonds count as a single in Vesper. So 1, 2, 3 bonded pairs, 0 lone pairs. So 3 bonded pairs, 0 lone pairs, trigonal planar, 120 degrees. Okay, so both C's are trigonal planar at 120 degrees. So if we were to draw them, we need to draw them connected in their proper shapes. So what we're going to have here is we're going to have a C double bonded to this C with a BR up here, a BR down here, a BR up here, and a BR down here. So that's the proper Vesper shape for this particular compound. So when we go to draw the valence bond diagram now, we have sigma, 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 pi for the first one, and sigma, 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 pi for the second one. So we're going to draw a sigma here, a sigma here, and a sigma here. So that's this carbon. Single is, so this sigma is going to be this one. This sigma is this single bond, and this sigma will be this single bond. But now we need to bring in this double bond. So we're going to put in our dotted P, and the other end of the P you can put wherever, put the dot in there. Okay, so now let's bring in the other carbon. So the other carbon is going to be the same thing, just a mirror image. So it's going to have its sigma bonded here. So that's this one. It'll have its sigma up here. That's that one. And this one over here. That's to that bromine. And then you want to overlap its P. So it's going to look like that. So now you have this here is your double bond. And it consists of an overlap of a sigma from each of the carbons and an overlap of the pi's for the p orbitals from each of the carbons. So you need you have a sigma and a pi bond. That's what makes a double. So a single are 4 sigmas. Then here we have a sigma, 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 pi from this carbon, sigma, 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 pi. So you get a pi bond in here and your sigma bond in there connected together. And now you just add your bromines. Bromine has, just like the chlorine and the fluorine, is the same thing. It's a half full p orbital with 1, and then you put your 3 lone pairs around it. Your half full p orbital. Whoops. I put the electron dot in the wrong spot there. I'm sorry. here. Okay. So we'll put it in here and then pair, pair, pair. And then the same thing here, a bromine with a dot. And this one here is your bromine in there. So you don't have to worry about the other end of those p orbitals, just pretend they're not there, but you have to draw them in anyway because the pi bonds are p orbitals and p's are full bow ties. So that's your valence bond diagram for this structure here. And you can see you have a double bond, 2 singles around the outside on each of them. Okay? So let's do an ion, the carbonate ion. So this would be number 5. So let's do CO3 2 minus. Okay, so we have a carbon with 4, and then we're going to do an oxygen 1, 2, 3, 4, 5, 6, oxygen 1, 2, 3, 4, 5, 6, oxygen 1, 2, 3, 4, 5, 6. So the 2 negative means we're going to add 2 electrons. So let's add 1 over here, and it has to go to the oxygen because oxygen is more electronegative than carbon. We're going to add 1 here. And then, so here's what you're going to notice. Single bond to this O, single bond to this O, and now all of a sudden you've got to create a double bond with this O. So you are creating 3 of your sp2s and an unhybridized p orbital to make your pi bond. So you need 1, 2, 3 plus a p. So when you look at your promotion, you're going to promote this up here. You have an S plus a P plus a P plus a P. You're only going to mix in 3 for 1, 2, 3, and then your double bond will be this one. So you have 3 sp2s here. When you go to Vesper, you again, notice you have the double counts as a single, so you have 3 of these bonded pairs and 0, and we know that 3 and 0 is trigonal planar. My pen's dying here, 120 degrees. Okay, so what we'll do is we'll draw 1 here, we'll draw 1 up here, and 1 up here. It really doesn't matter as long as it looks like your 3-leaf clover. Okay, and now we're going to bring in our oxygens. So this oxygen here, we filled its second p orbital, so it has 1 p that's half full. That's going to come in. Same thing with this one, 1 p that's half full. And now, when you look at this, this oxygen has to double bond. Well, we've only got 1 bond here on our carbon. So now you've got to bring in this unhybridized P, this pi bond. And it really doesn't matter where you put it as long as it's on the same side as this.